My poster is about an elevated supercell that was observed during VORTEX2. And if you don't know what an elevated supercell is, it's a supercell that's situated over some sort of stable layer. The boundary layer itself could be fully stable, or it could be an inversion, like it is in my case. Now these types of storms typically don't lead to tornadoes, but they still have other high impacts, such as heavy rainfall, hail, and occasionally strong winds at the surface. So these storms are not very well documented either. There's very few data sets. This data set we have from VORTEX2 is actually one of the highest density data sets known to date. So what we did is we took observations from that VORTEX2 case. So we have mobile Doppler radar, sticknet, and mobile mesonet observations at the surface. And we looked at all this data and also created a model sounding from the observed soundings from that day to try and learn more about the processes of an elevated supercell, as they're not well known. So if we look at the observational analysis, you can see from these radar images over time the storm is fairly steady over the course of an hour. And it's also got this interesting hook feature here. So going more in depth with it, you can see from the dual Doppler analysis here that below the stable inversion, which is roughly 2 kilometers in height, the storm doesn't seem to be affecting the surface winds. So the storm is decoupled from the surface as you go higher up in the atmosphere. Winds start to increase and change direction. And this is significant as it shows that the storm is indeed elevated. And the other interesting thing we pulled out from our dual Doppler analysis is that there seem to be these wave features on the inversion that may be helping to play a role in lifting these parcels to their LFC and maintaining the storm's updraft. And finally, the last thing we saw from the observations at this point is that there's cooling at the surface that's evident in the theta observations from the mobile mesonets, but there's no cooling from theta E, which implies that there's no downdrafts from the mid-levels reaching the surface, and that the stable layer is acting to slow the downdrafts before they can reach the surface and produce severe winds. Another sign that it's elevated. So, like I said earlier, we took the observed soundings, made a model simulation, a model sounding and radar simulation from that using CM1. And as you can see, if you compare the simulated reflectivity with the observed reflectivity, they're fairly similar. So our model appears to be up to shape. And the main points here is that we were able to look at vertical vorticity in the mid-levels to prove it really is a supercell. There's no vorticity at the surface, which signifies that it's elevated as well. Again, these wave features show up in the theta surfaces here in the model around the same height as in the observations, so we think these are gravity waves or some sort of waves helping to lift parcels to their LFC. And another big thing that we saw was that air in the updraft is being lifted from above that inversion, so this 1.5 to 2 kilometer layer in the model with this tracer concentration, warmer colors are more air that's being pulled from that level. So all of the updraft origin is above that inversion. Again, the main conclusion here is that all of these signify that this is indeed an elevated supercell. There's significant vertical vorticity in the mid-levels, but not at the surface. The updraft air is coming from above the inversion. There is cooling underneath the storm, but that's due to evaporation, precipitation, not penetrative downdrafts, and the storm is decoupled from the surface. So for future work, we're going to continue to work with these observations, try to make them as useful as we can, continue working on model simulations and try to produce severe winds at the surface with this, and also do a more in-depth analysis to try and solve the mystery that is the elevated supercell and get a nice baseline study for these types of storms.